Hello, and welcome to Physics 2, Lab 3, Bar Magnets. Introduction. The purpose of this lab was to observe the magnetic field produced by a bar magnet, then to create a computational model of the magnetic field at different points about the magnet from these observations. Then we can showcase this computational model under the given assumptions and understand the effect the magnetic field has on different points about the bar magnet. The physics principles used in this lab were Newton's third law, which states for every action there is an equal and opposite reaction, and the law of Biot-Savart, which describes the magnetic field produced by a wire carrying a constant current. The equations used in this lab were the equation for magnetic moment, which states mu equals AI, the equations for the magnetic field perpendicular, the magnetic field parallel, and the general equation for the magnetic field, as well as the property of superposition. Here's a preview of my results. And models. There are two models in this lab, the first of which is the observational model. This was created by using a Magnetar app to measure the magnetic field produced by a bar magnet, which was first compensated and aligned to Earth's magnetic field. These values for the magnetic field at various positions perpendicular and on axis to the magnet were then recorded in my physics notebook. The computational model was made in GlowScript code, as always, used the quantitative data gathered in the observational model to simulate a magnetic field and the magnetic field at various points about the magnet. Experimentally, the recording, as mentioned, all the values from the magnetometer were recorded in my physics notebook. Computationally, the measured magnetic moment of the bar magnet was 1.465 joules per Tesla, and the distance that each point was measured away from the magnet was roughly 0.15 meters. Computationally, in the computational model, again, it was created in GlowScript code to compare the experimental data to an accurate simulation. So, going into the code, we have our magnetic moment here. We have a function which defines the dipole moment of, not the dipole moment, but the magnetic dipole of the bar magnet at each observation point that we will be utilizing. And for this function specifically, we utilize the general equation since we aren't only using perpendicular observation points or parallel observation points, we're using any observation point. And over here we have our observation axes. So on axis, of course, in the x and negative x direction, perpendicularly we have positive y, positive z, negative z. Here we define our on-axis vectors in the color orange. We have our perpendicular vectors in the color cyan, and then we have a singular vector which is 45 degrees from the magnet, and that is in magenta. So as a result, we can see that the vectors that are on axis are facing the direction of the magnetic moment. This vector is not on axis. It is actually perpendicular. I was unable to rotate the simulation properly to showcase that disparity, but all of the perpendicular vectors, as you can see, are going in the opposite direction of the magnetic moment, and this magenta vector up here in the corner, which is 45 degrees away from the magnet, if we were to have a bunch of them going around the magnet, you would see that it goes in a clockwise motion about the magnet. So, discussion. What if we didn't compensate for magnetic north? Well, if we didn't compensate for magnetic north, the measured values in both the x and y directions would differ because Earth's magnetic north would superimpose with the field of the bar magnet, which would then skew the measurements in the direction of the angle made between the magnetic moments of each magnet. And another what if you stuck two of these magnets together? What would happen? Well, you could estimate that the new magnetic field produced by the magnet would be double that of the original. And you can say that because if both of these magnetic moments are going in the same direction, when you look at it very far away, utilizing the monopole theorem, you can just say it's one object with a magnetic moment of 2 mu, thus doubling the magnetic field. And In conclusion, this lab showcased the effect and importance of magnetic fields and how the position of the magnet and the point it is observed from can affect the magnetic field and how it impacts an object. Thank you for watching.